These are select problems from Chapter 4's homework and their solutions. I'll let you read this problem through. It's quite long, but essentially what this problem is asking you to do is convert a number from base 10 to base 2. It explains this whole idea of robots and how robots and the computers use a binary system, and millions of little switches are either on or off, represented by ones or zeros, to convert the number 21, which is a base 10 number, into a base 2 number. We're going to start with the number 21, which is the base 10 number, and look at the place values for a base 2 system. The first place value would be 2 to the 0. This represents the ones place. Next place value is 2 to the first, represents the twos. 2 to the second. And I'm going to create these different columns until I come across a power of 2 that is just bigger than 21. So I have now 2 to the third, which is the 8s, 2 to the fourth, which is equal to 16. So these are all values that are still smaller than 21. But my next power of 2 is 2 to the fifth. This is equal to 32. This is the first place value that's bigger than 21. So I'm going to start here. Again, I'm creating my columns here. Since 32 is the first number that's slightly bigger than 21, I'm going to cross that column out because I'm not going to use that to find out the value of 21 in a base 2 system. But it does help me identify where do I need to start to begin this conversion from base 10 to base 2. So I find the first column that's slightly larger than my base 10 number. Again, that's my base 10 number is 21. The column that's larger is 32. And I begin grouping with the column that's just to the right of there. So I'm grouping in terms of 16. 21 only has one group of 16 in it. If we look at 21 and remove the 16, we're left with the value of 5. We now have to use these place values in order to come up with that value of 5. Well, 5 is less than 8, so we know there's 0 groups of 8 in 5. But 4 is less than 5, so we're going to use that as one group. When I remove 4 from 5, I'm left with 1. 2 is bigger than 1, so I use this last column to represent the number of ones. 21, represented in a binary system, is equal to this number right here, which is 10101. So again, number 21 in base 2 is 10101. Express the given Hindu-Arabic numeral in expanded form. 6,373,548 is 6 million plus 300,000 plus 70,000 plus 3,000 plus 500 plus 40 plus 8. We can rewrite this as 6 times a million. That would be our expanded form. Or this is one example of expanded form, but we're going to express this using powers of 10. So 6 million is the same as 6 times a million plus 3 times 100,000 plus be 7 times 10,000 plus 3 times 1,000 plus 5 times 100 plus 4 times 10 plus 8 times 1. This is expanded form. We can see in each of the terms which power of 10 is being used. We could take this even further using exponents to represent this expanded form, which would be 6 times 10 to the 6th for the millions, plus 3 times 100,000 would be 3 times 10 to the 5th, plus 7 times 10 to the 4th, plus 3 times 10 to the 3rd, plus 5 times 10 to the 2nd, plus 4 times 10 to the 1st, plus 8 times 1. But remember, 10 to the 0 is the same as 1, so that 1 is representing 10 to the power of 0. This second form, right here, is also expanded form, but it's expanded form using exponents. Express the given expanded numeral as Hindu-Arabic numeral. So here we're given a number that's been expanded or is in expanded form, and we're asked to rewrite this in a number that we would see every day, Hindu-Arabic or base 10 number. First thing I'm going to do is express this and expand out the powers of 10 so I know what it is I'm looking at. 6 times 10 to the fourth means we have 4 zeros after it, 10,000, plus 6 times 10 to the third means 6 times a 1 with 3 zeros after it, which is 1,000, plus 3 times 10 to the second is 3 times 10, or sorry, a 1 with 2 zeros after it, plus 6 times 1, which is just 6. 6 times 10,000 is 60,000, plus 6 times 1,000 is 6,000, plus 3 times 100 is 300, and then plus 6 gives us 66,306. This is our Hindu Arabic numeral. Express the given expanded numeral as Hindu Arabic numeral. To begin to express this, we're going to first expand those powers of 10 to see what they look like. 8 times 10 to the negative first means we have 8 times 0.1 plus 2 times 10 to the negative second. 10 to the negative second is 0.01 plus 3 times 10 to the negative third is 3 times 0.001. 6 times 10 to the negative fourth is 6 times 0.0001. Simplifying each of these terms, we end up with 0.8 plus 0.02 plus 0.003 plus 0.0006. This gives us the Hindu Arabic numeral 0.8236. This problem essentially is asking us to convert 49, which is a base 10 number, into binary. To accomplish this, we're going to start with the binary system and list the place values until we come up with a place value that is just bigger than 49. I'm going to start with 2 to the 0 power, 2 to the first, 2 to the second. 2 to the 0 is equal to 1, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16. We still don't have a place value that's bigger than 49 yet, so I'm going to continue. 2 to the fifth, 32. 2 to the sixth is 64. Here, we finally have a place value that's larger than 49. Create the columns here. To identify 64 as being the column that's just bigger than my number, I marked that out because we're not going to use that. And now I'm going to start regrouping 49 based on these place values. So using the column that's just to the right of 64, which is 32, we have 49. There is one group of 32 and 49. If we look at 49 and remove that group of 32, we're left with 17. The next column is 16. I have to represent 17, so I'm going to use one group of 16 to help me represent 17, and then I'm going to remove that group of 16 from 17. I'm left with just 1. The column after 16 is 8. I only have to represent 1, so this column is too big. I'm not going to use it. 4 is bigger than 1, so I'm not using this column. 2 is bigger than 1. Cannot use this. And my final column, which is the ones column, I'm going to use 1, 1. 49, a base 10 number represented in binary, is 1, 1, 0, 0, 0, 1. Whereas to convert the given numeral to a numeral in base 10, this given numeral is 332 base 4. When we make conversions from given bases to base 10, what's important for us to know is how many decimal places are used in that numeral and what does that base system look like. So here, our number 332 base 4, we have a base 4 system and we have 3 place values. So in order for me to make this conversion, I'm going to look at those 3 place values base 4, starting with 4 to the 0, 4 to the first, 4 to the second. 4 to the 0 again is equal to 1, 4 to the first is 4, 4 to the second is 16, and this number that I'm given, 332 base 4, means we have 3 16s plus 3 4s, 2 1s. This is, in order to make that conversion, we're going to take the leftmost column, 3, and multiply it by the place value, 3 times 16. We're going to add to it the next value, which is 3, and multiply to it its place value, 4. Finally, we're going to add that last number, 2, and multiply to it its place value, which is 1. Simplifying this, 3 times 16 is 48. 3 times 4 is 12. 2 times 1 is 2. If we add this together, we end up with 62. 332 base 4 is the same quantity as 62 base 10. Convert the numeral to a numeral in base 10. The given numeral is 11010, and it's in a base 2 system, so it's in a binary system. We have to convert this to a base 10 system. So in order to do that, we're going to set up the base 2 system with 5 place values, starting with 2 to the 0. Next one is 2 to the first, 2 to the second, 2 to the third, and 2 to the fourth. 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 to the third is 8, and 2 to the 4 is 16. These are all the place values I need in order to make this conversion happen. Once I set this up, I'm going to substitute these values that are given to me into this place value system and then evaluate. So I have 1, 1, 0, 1, 0. And to evaluate, I'm going to multiply the digits in those place values, the value of the place value. So the first one is 1 times 16 plus 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1. This is the same as 16 plus 8 plus 2 plus 1. 16 plus 8 is 24, plus 2 is 26, plus 1 is 27. Use divisions to convert base 10 numeral 1215 to base 6. To begin this, we're going to look at the base 6 number system and identify the first column or place value column that's larger than 1215. I'm going to start with 6 to the 0. This is the ones place. 6 to the 1, this is the 6th place. 6 to the second, this is the 36th place. 6 to the third is the 216th place value. We still haven't found a place value that's larger than 1215, so I'm going to keep going until I do find that place value. 6 to the fourth is 1296. This is the first place value that's larger than our numeral. I'm going to block this section off, or this place value off, because we're not going to use that. We're going to start with the place value 216. We want to know how many 216s are in 1215. We're going to use division to find this out. 1215 divided by 216 is equal to 5.625. Ignore the decimal expansion part and just look at the whole number value, the 5. This tells us it takes 5 whole 216s that are used to represent the quantity 1215. 216 times 5 is 1080. This first column represents 1080 of our 1215. We're going to subtract that from our numeral, and we end up with the difference of 215. Now, using our very next column, which is the 36 column, we want to know how many 36 are in 215. So again, we're going to divide 215 divided by 36. This is equal to 5.972. And again, ignoring that decimal expansion, we just look at the whole number. This tells us there are 5 36s that are used to represent this quantity. 36 times 5 is equal to 180, and we're going to subtract that from our 215 to find out how much more we have to represent in this number. 215 minus 180 is equal to 35. So using our next place value, which is 6, we're going to see how many 6s are in 35. I'm going to do that over here on the side. 35 divided by 6 is equal to 5.833. We can again ignore that decimal expansion and just use the whole number, so there are 5 6s that are used here. 6 times 5 is 30. We subtract that from 35. This leaves us with 5 more units that we have to represent. So using our very last column, the ones place, to represent those remaining 5 values, we end up with 5 here in the ones place. So our conversion, 1215 base 10 into base 6 system, is 1215 base 10 is equivalent to 5555 base 6.